Hi, welcome back for the final session. So similar to the one on drawing the contours for the internal forces, I'm just going to begin this session on drawing the contour plot for the normal stresses by noting that obviously the stress is going to vary through the thickness or through the depth of the element. And that'll be a function of the axial force and also the bending moment. But the way that we're going to plot it is we're going to do something very similar to when we were plotting the internal forces rather. But this time we actually want to put a series of quadrilaterals through the thickness of the element. So what I've indicated here is just basically the mesh, remembering that the mesh is only for display purposes that we're going to construct. We will be able to vary the number of these quadrilaterals through our thickness, but each one we want to end up with the point and also the value numbering so that we can input it 0, 1, 2, 3, 0, 1, 2, 3 and so on. And I've just indicated here, these are sort of quadrilateral numbers, if you like. So for each element going between the start node, node A, and the end node, node B, we want to have a number of quadrilaterals through the thickness, and in this case I've obviously shown 4, so we would just number these going between minus 0.5 times the thickness and plus 0.5 times the thickness as 0, 1, 2, 3. So having given that explanation, we can now just move on to actually draw the contour plot for the normal stress in this case. Okay, so we're going to need to bring in quite a lot of information that we've previously derived in the Grasshopper definition. So I'll start off, the first number that we want to bring in is the thickness. So obviously we do have that already, but I'll just label that as the thickness. And again, this will be in millimeters. So we'll just zoom out, go and find the information that we had. So remembering that that will be the depth, just bringing that down like so, and we can just hide the information here so that we don't have wires running all over the place. I'm just going to double check that actually we bought this one from the correct component. Yep, so we did. And actually I'll just double check that I've taken this from the correct component. So I've accidentally taken it from the second mode area. So I'll just correct that and bring down the depth or the thickness. So the other information that we're going to want in order to calculate normal stress, so sigma xx, going back to our structural mechanics knowledge, so we need the cross-sectional area, so we'll bring that in a second, and we also want to have the second moment of area. So going up here again, so 1 is the area, so that'll be the area there, and then the other one that we want is the second moment of area, so now coming from second moment of area, so we can bring it down like so, and I'll just group these and say that that is area and IYY. At this stage we'll leave it for the second moment of area. I'm going to turn the bifocals off just for a little while because it will get a bit tricky with labeling everything. And as before, I'm just going to hide these so we don't have too many wires just going all over the place. So the next bits of information that we want is we obviously want the axial force and the bending moment at both the start and the end nodes. So we're going to have another two sets of numbers coming in. So like so. And for these, we can go back up to where we divided everything down. We want to go before the gated stream, so obviously we're not selecting one in particular. So I'm actually going to go back from before the relay. So we have list item 1. This will be the axial force, or list item 0 really. So this is the axial force at the start node. Then we want the bending moment, which is going to be this component here. So we'll bring the bending moment down to here. And then we need to just repeat that process for the end node. So bringing down the axial force from there. And then the bending moment from there. So we almost have all of the information that we want now. So I'll just group these and say F X, the axial force, and then Y for the start node. And then these are the ones for the end node, so just labeling them Fx again for the axial force and My for the bending moment, so for the end node in this case. And what we're about to do is put all of this information into an expression so that we can calculate the value of the normal stress, sigma xx, for whatever depth we are or whatever distance through the thickness of the cross section we are. So the expression that I'm going to use is the one that you've probably used as far back as first year. So we know that Fx divided by the area plus My, in this case, multiplied by the value of z divided by Iyy will give us the stress, sigma xx, that we're looking for. So that's our expression there. Obviously we need to gather all of the input in the way that I've indicated I want the input. So we have the cross-sectional area, the second moment of area, and then we're going to have Fx, so the axial force, My, the bending moment, and then finally, so we haven't yet divided things up, but our z coordinate is the other information that we want. In terms of the output, I'm just going to label this as sigma xx, so indicating that it's the normal stress that we're outputting. So I can connect up my area and my second moment of area, and then actually what I'm going to do is just copy this. So I want those connections, so I'm going to do the calculation for the start and the end node effectively at whatever z coordinate we are through the depth of the cross section, and then I'm just going to connect Fx and My up for the start node, and then similarly for the M node. So the next part we're going to look at is how we decide on this z term and what we're going to do with that. So for that, it's a little bit similar to how we split up the beam in the first place. So I'm going to put in a panel, and this is basically the number of quadrilaterals that I want to generate through the thickness of the beam, remembering to make it multi-line data again. I'm going to refer to this, just grouping it and then giving it a label. So I'm going to refer to this as the number of bins, but it obviously could just be the number of quadrilaterals, for example. I need to make sure that this is an integer, so I'm just doing that. Obviously we couldn't have a decimal place there. And then what I'm going to do, as I mentioned, a little bit similar to before, so I'm going to set up a series, and the start I want to be minus 0.5 times the thickness. So I'll put in just another panel to allow us to do that, and minus 0.5 there. Just to convert that to multi-line data as well. So that will feed in here. We want that as the start. Then, depending on the thickness, obviously I want to feed that in a multiplication component in a second. But in terms of the sequence that I want, so the series, so for the number I want to, or the step size rather, I want to do 1 over. So I have my number of bins, and I can just pop that in there like so. Let's tidy everything up a bit again. And then the total count, so I can feed the 16 in there. And what I observe here is that I end up with 16 points, and I would actually like the plus 0.5 to appear in there as well. So I'm just going to click on this, and normally you might do this outside, but actually I'm just going to do it as an expression editor to the input of the component, and so that is now 17 coming in there. So we can see we have a series going between minus 0.5 and plus 0.5, which we obviously then want to multiply by the thickness. So I'll do my multiplication in here. So I have the thickness coming across this series component. And then the other thing that I'm going to just add here is I'm going to keep the same thickness magnification that we had developed up there. So from here, you can now see that we have a set of Z coordinates basically, and obviously we're now going to feed them into the expressions. So like so. And obviously that then just nicely removes any issue that we might have going on. Okay, so we have the values that we're interested in, but we don't yet have the points where we want to be able to associate those values with. So the next thing that we need to do is define a line going up and down between minus 0.5t and plus 0.5t at each end. So I'm going to go back here, and these are basically the points that we need. So I will just need to bring them in here. So taking them after we've exploded the tree. So we have one lot from there, and then the next lot from there. So that creates our series of lines you can see over here in the preview. And then similarly for each of the end nodes, we take our data from here. So we have another set of lines there. And then what we want to do is we're going to use a divide line component. So divide curve here. We could have used the shatter component as well. So this is just another way of achieving something quite similar. So I can run my line in here, and then actually I am going to run the number of quadrilaterals or number of bins into here. So that then gives me a total of 17 points coming out of there, and those are the points that we're interested in, and we'll just arrange the data in a minute or so to do what we want. So we're going to do the same for the next one, so for all of the end lines, if you like, and again just taking that component from there. So now, obviously, we need to form these into our quadrilateral definitions. So one way that we can do this is we can use something called a shift list component. And what that allows me to do is it allows me to pick up basically the component from one index along in the list. So that's going to allow me to take, the 0, 1, 2, 3 sequence of points that I referred to at the beginning. So we can take our points over to here, like so. In each case, I then just actually do want the shift offset of 1. That's the default here. And again, I probably wouldn't need to do this, but I'm just going to make sure that the wrap function is turned off to make sure that I'm not sort of accidentally picking up anything that I don't want to. And the final thing that I'm going to do is just use a shortest list component. So this basically trims things so that we don't end up with more points than we need after having done that shift list command. So I can just connect the first lot up there, second lot up there. Again, same down here for the end node. So just connect the first one there, second one there. And then what I'm going to end up with is I've now reached the stage where I can do the weave command that we've used before. So just increasing the number of inputs. I'll leave the pattern alone at the moment, but we know we're bringing things across like this and like so. And then actually the pattern that we want is the same as the pattern that we had up here. So using my panel, what I want, or in terms of the original number or the order that we're actually generating the points in, we want 0, 2, 3, 1. So just bring that across, 0, 2, 3, 1, and OK, and just convert it to multi-line data. I'm going to leave it just positioned down here because I know I'm going to do something similar with the values in a second. So I will pull that up to the pattern there, and you can see that we've got quite a complicated data structure. So what I'm going to do is just flatten all of that, then going to use my partition list command, and obviously it's 4 points that I want to define each of the quadrilaterals. So I'm just going to do like so, and then similar to what we did in the previous definition, I'm just going to simplify whatever output is coming from there. Okay, so we're going to move on to this lot here now. So doing very similar to what I did up here. First of all, I'm just going to use this shift list again. Like so. Again, the default of 1 is fine. And then I'm going to set the Boolean for wrapping the list just to false, as I did before. Then we've got the shortest list command. So bringing that there, and then this one across there. Like so. And then we're going to weave this data in the same way as we're doing up here. So just adding to the input that I need. The pattern is going to come from there. And very similar again to above. What we're just going to do is flatten that data. Then we'll need to partition the list as before. So the number will be set to 4, the integer value. Run the list in here. Again, this is not that complicated, but we are just going to simplify the output for the data. So what we now have is we have all of the points that we want, and we have all of the values that we're going to make into colors in a second. So we're where we want to be. What we can do, however, is I just want to make sure that the logic seems reasonable. So from here, I want to select a tree path. So a tree branch is what we really want. And that's just to make sure that one of these branches, so one of the sets of 4 points, are going to be feasible to form sensibly into a quadrilateral. So at the moment this is empty because I need to specify the path or the branch that I want to look at. So here I'm just going to right click and I'm going to set the path. So we do this between curly brackets. So I'm just going to set the path to 0, and that produces 4 points from there. So I'm going to do 2 things. One is I'm going to use the point command, and then we just want the point list, like so. Hopefully we won't need to alter the size, but we'll come back to that. The other thing that I'm actually going to do is I'm just going to use something called a polyline to check that the points in the order they're appearing can generate a quadrilateral. So this will output the polyline. And we can see, if we just zoom in on this now, so it is very thin. That makes sense. At the moment, you can see if we do the point numbers, so zooming in, we have what we would expect. So 0, then panning across. So you have to go a little bit of a way, just because of the length of the lines compared to the thickness of the cross section. So then we go to 1 here, then 2, and then if we go back, we can see 3 on here. If I opt to close the polyline, so just using this boolean, you can see it joins 3 back to 0. So that's a good indication that everything is working in terms of the quadrilateral that we'll use in a second or so. So that is included as some logic on the canvas that I've made available, and that's basically what I'm doing with that little collection of components there. Okay, so I'm going to use these points to generate a mesh, similar to how we did before. So construct mesh is what we want. So we're running these in as the vertices, and the face is made up of those points in the sequence or the order that we wanted, and that's the default. And then obviously the color is what we're going to be working on in a second. But if we just zoom out to look at all the components, you can see that we have that beam as we want, just running along here. So we're going to do, again, what we did above. The first thing we want to do is we want to find what our range is in terms of the actual values. So I'm going to flatten that coming into the number. And then we've got our bounds component, so just attaching that in like so. So then what we want to do is, having got our bounds, so this is running between -60 and +60 for the megapascals. This will be for the normal stress. So I want then to deconstruct the domain as I've done above. So we have that information coming in there. Then we want our gradient component again. So I'll just run those in as the start and the end values that we're interested in. And something that we can do is, you can see that I double clicked on there. And what this allows me to do is it allows me actually to edit the domain. So I would like it so that compressive stresses are in blue. That's what I normally use. And then tensile stresses are in red. So if I select this one here, and then what I want to do is just take that as blue, and then select this one here, and I just want to take that as red. And actually I want to alter the second color that it mentions as well, so I'll just go back and do that here. And then the final thing I want to is, I actually want to add a midpoint, so that if the stress is quite low or close to zero, then I want it just to show basically in white. So I can pull this across and I get another point like so. So it was just that and pulling it on. If I click on this point, so I actually want it bang in the middle, so I can say 0.5 there. I want it to be white, so like so. And then this is basically the color gradient that you'll see in an awful lot of more commercial FE packages or structural analysis packages. What I can also do is, under the presets, I can just say add current gradient, and then when I come back to this definition in the future, it'll be there as something ready to use. So before we move on to the labeling, I've got my mesh component and I've got my colors here. I can now just connect the values up to the T input, and you can see, if we zoom in now on the beam representation that we have, so we have what we would expect for the cantilever. So we have compression at the bottom, tension at the top, and if I zoom out, then what you can see is, as we approach the free end, so basically as the moment reduces, that stress reduces down to zero at the free end. So that's what we would expect, and then it gradually increases as we get towards the fixed end support here. Okay, so for the labeling, I want to be able to label the stress at the bottom of the cross section, but also at the top and also potentially at the middle. So in this example, we just have a bending moment, so the axial force is zero and won't be contributing. But if we did have a larger axial force, then we might have a non-zero value of stress at the middle. And so I'd just like to be able to pick that up in terms of the labeling. So we're always going to look at the start node, just to sort of avoid complication. So in terms of the list of points that we're interested in, it's going to be the list of points from back where we did the curve division, so coming in there. And then in terms of the list of values that we're interested in, it's going to be similar. It's the list of values coming back from there. So these are the points and the values that we're interested in. In order to get the top and the bottom, what I can actually do is I can do a list item, and I'm going to be able to select on the top and the bottom for each of them. And the way I can do that is just running the list in. So I is effectively the bottom, and then I minus 1, so coming in here, doing this will effectively give me the value at the top. So I'm going to do that for the point, but also for the value. So just like so. Okay, so I then want my text tag. So there we go. So I'm going to have 3 of these. So 1, which would be for the start node at the bottom. 1, which I'm going to say is for the start node at the top. And then 1 actually that I'm going to say is for the start node in the middle. So we have all of those. I'll just get the tag command. So those are our locations. So in terms of the location, the I there, so just the index, so the start of the list, obviously I there was the default of 0. So that will be my location. For the top, that's my location. In terms of the text, I'm going to format this. So I'm going to do that by using an expression. So the expression that we want is, oh, shouldn't have got rid of the format there. So we want to do as we did before. So F2 in here, and again you would be able to find out further information about the sort of nomenclature for this. And obviously for the stress, we're going to put that in megapascals, and then we just have X as the input that I'm interested in. So I can take away that Y input, and obviously here it's now the number that we're interested in. So for the top, that's the number that we have. So that's the text going in like that. Copying this, so Control V or Control C and then Control V. So rather this one is the bottom, this one is the top. So I can run that in like so. Just going to pull that. Actually, no, we'll leave that there. So if we want the value in the middle, what I'm going to do is just merge and then use an average component here. Okay, so I'm just going to pull that up out of the way. So we want to merge the values at the top and the bottom, and then take the average, and I can do that whether it's a point or whether it's a value. So that will give me the middle location. Tidy these up a little bit. Control C, Control V to get me the format that I want things in. So I'll just pull that back slightly. So again, I'm going to use a merge component. So again, taking top and bottom in this case, and then the average value. So I'm just going to pull some of these components a little bit along, just so we can create a bit of room. So we'll just move them along like so. Let's pull these back here. So we now just need to run that average component in here. So that's the text. So just to label up, so these are the values at start node at the bottom. So that's basically the first point in the list. These then are the values at start node at the top. And then finally, these are the values at start node at the middle. So I can then just group these, so and labeling, so this gives me the diagram and values at bottom, middle and top. Okay, so I can now just group all of these. So just don't want the bifocals, so I did Control, just allows me to keep that out. So I'm going to group them. I'll move the whole group down a little bit so that our labeling is clear, and then I can just call this contour plot of the normal stress sigma xx. So for our cantilever, I just want to make sure that this all seems reasonable, makes sense. So we were able to look before at the stress distribution through the thickness, but let's just check the values are listed correctly at the bottom. So you can see there we do have minus 60 MPa down at the bottom. If I show the value at the top, we have plus 60 MPa up at the top. And then if I show the middle, you can see that as 0 MPa at the middle. Final thing that I hadn't included before, so we just want our color swatch, and again I want to set the text as black here, so we can do that like so. I'll just shift and then add it to the group, and I'm going to just set all of those black, so we can then just see the mesh, and again we can see the values quite clearly, so that all makes sense. If we sort of look along, we can see how these values are reducing as we go along the cantilever, and if we go right to the end here, so these are obviously the values at the start node of the final element. I haven't listed the values at the final node, but we can see from the color that essentially the stress has dropped to 0 at that point. So the very final thing we can do is just a little bit of processing of the values in order to get out what we're going to call the apps max stress. So obviously we're doing all of this to see whether material is likely to yield or not in the structures that we're analysing. So that's why it's of interest to find the apps max stress, to see if it exceeds a yield stress value. Okay, so for the absolute max stress, what I'm going to do is bring across these values, so those at the top and the bottom. So it'll always be the extreme fibers that the absolute maximum occurs in, and I'm just going to absolute both of those. So there is a maths component that'll give me the absolute, so I can just run that one in there and that one in there. Just trying to take care to note which is going to be the top and the bottom. So this one is our top and this one is our bottom, basically. I need to flatten the input to that, so I'm just going to flatten the input like so. And then what I need to do, so I notice on the canvas, I just brought these across a little bit differently, so I brought them in as numbers before I did the absolute. So I'll just connect these up. Obviously, we don't need to flatten if we're going to flatten the number, so I'll just flatten the number like so. Flatten, there we go. And again, noting that I'm bringing across the top there and then the bottom there. And what I want to do is I want to basically see which of these is going to be the important one, so which has the maximum value. So I'm going to use a greater than command, and I basically just want to know if the value is greater than 0 or not, or rather at the moment I want to know which of the two values is 0. So don't really need to do this, but I can just make sure that this is definitely flattened, so I can run this in like so. And what that'll tell me as the output from here is it will tell me if input A is larger than input B, and obviously I want to just select the one that's the absolute maximum there. So we can use a pattern selector. So pick and choose rather is actually what we're after. So I'm going to run my actually greater than equal command in there. So what we're saying is if the top is greater, we're going to put it into that list, and if the bottom is greater, we're going to put it into that list. So this will allow me to do the picking and choosing now. And we want to do the same in terms of the location that we're looking at. So again, pick and choose component like so. Again, the information that we're interested in is that pattern, and this time obviously the point comes from here, so keeping them the same way round, so we have top or bottom. I'm going to flatten both of these coming in, so obviously these ones have already been flattened back here. So this results in a series of 8, so we had 8 elements originally, and similarly we have 8 stress values here. So I want to format it in the same way as these, so Control C, Control V, so I can bring that down as my format, which is what I want in here. And then finally I can do my text tag again, so just need to type in tag to reliably get it. So text tag, my location is there, my text is there, just bringing across the swatch color again. So selecting these components, I'll just do shift to include that one. So I want to group, and I'm going to label that group just as find the apps max stress. So I'm just putting it in quotes to indicate that that's what it's generally called within finite element packages. So what we can now see is if we select the diagram, we have what we're expecting, and for this it's sort of it doesn't really matter whether we pick up the top or the bottom value. Because of the way I've set this group of components up, it is actually always just going to pick up the top value. But if we had a situation where there was an axial force as well, it would just pick up whether we were interested in the value at the top or the bottom. Okay, just labeling this text tag as well. So this is the apps max stress at top. Well, I'll just stick with what's on the canvas that I've shown you, so at bottom or top. The point is this takes into account the stress due to the axial force and also the stress due to the bending moment. So that finishes the Grasshopper script for the Grasshopper definition rather, for the beam example. I think the point here is that you now have a structural analysis package that really does everything we might want to do with beam elements in 2D. What I would strongly encourage you to do is now try and put in previous examples that you've had for structures. So it might be from the stiffness method, flexibility method, and so on. But also what I'll do is I'll provide a series of examples that are actually included in the Steel Designer's Manual. So these are standard cases, and before structural analysis was a little bit easier to carry out. These are cases that people would refer to in order to calculate, say, the maximum bending moment or the maximum deflection, axial force, and so on. So I'd encourage you to work through some of those examples, because obviously I know for many of you, you will have got to this stage and you've built the definition. You've included the Python component, but you now really want to explore it and check that it's giving the results you would expect. And then once you've sort of contented yourself that it's giving the results you would expect, I would encourage you to put in some kind of novel structures and see if there's sort of some interesting things you can find about that. One of the things that can be quite interesting is if you put in a simply supported beam, but then move the supports towards each other and see if you can reduce the value of the maximum bending moment. So you might be going, in that case, from a bending moment at the middle to actually, so that would be a sagging bending moment for a simply supported beam, to having a bending moment that's a hogging bending moment over the supports, and that's something that's worth exploring to see if you can find the optimal position for the support. So that's one of the examples that I'll provide. Okay, I think really just see how you get on, and please do find myself or the GTAs if you get stuck at any point along the way. But what we have now is an entire definition that, as I say, basically does the job of relatively simplified but a structural analysis piece of software in 2D. So just looking through, I spotted a slight issue. So one is we should just remove that comma from here. So this was on the first, where we were generating the bending moment, shear force diagrams, and so on. But we can see in Rhino the preview, that's all working as we would expect. Moving on down just to look at the contour plot. So again, that's working as we would expect. I'll just control so that we can deselect those. So we have the contour version of that diagram. And then finally, we had obviously through to the stress distribution here and the apps max values like so.